Welcome to this college algebra video on solving exponential and logarithmic equations. To begin with, I want to remind you of a few basic facts and properties about logs. First fact is that b to the log base b of x simplifies to simply x. In the last section, we used this property to solve some equations. We said that in a sense, raising something as a power of b cancels out the log base b. Next property is that log of b to the x can be written as x times log of b. That is, that exponent x can be brought out in front of the logarithm. The same is true for natural log of b to the x. It is equivalent to x times natural log of b. In fact, this property is true for a log of any base, but specifically, we're going to see it in this section used with log base 10 and natural log, the log base e. Here are a few concepts that you'll need to remember when you're solving exponential and logarithmic equations. Number one, isolate the log or exponential part first. One side of the equation should only be an exponential expression or a log expression. If there's anything added on or multiplied on, we need to get rid of that first. Second, logarithms can undo exponentials. So when we start with b to some exponent, usually the variable is up in that exponent, equals a, we are going to do a log of both sides of the equation. I usually will use natural log, but you could also use log base 10, or you could really use any log of your choosing. This allows us to bring the exponent, where that variable is, out in front of natural log. It's kind of like we get it onto the regular playing field with everybody else. Number three, exponentiating undoes logarithms. This is the concept we saw in the last chapter. And for these, we always want to use the same base as the log base. We've seen examples with common log, log base 10, natural log, log base e, but we'll also see an example with a different log base. For our first example, we're going to solve the exponential equation 3 to the x equals 15. In the past, we've solved equations like this using guess and check or the equal base method, but let's use a more general problem-solving method. That is, we're going to take the log of both sides. I'll use natural log. Natural log of 3 to the x is equal to natural log of 15. This allows us to bring that x out in front of the natural log. So now the equation is x times natural log 3 equals natural log 15. Well, this is just x times some number equals some other number. Divide both sides by natural log of 3, and we have our solution. X equals natural log 15 divided by natural log 3. This is an exact answer, and in many cases, it's okay to leave your answer in this form. When we're solving word problems in context, we may want to enter this into a calculator to get a decimal value. Here's another exponential equation. 5 to the power 2x minus 1 equals 2.5. Let's take the log of both sides again. And just because it's the habit I'm in, I'm going to use the natural log, but you could use log base 10 as well. Natural log of 5 to the 2x minus 1 equals natural log 2.5. This allows us to bring the power 2x minus 1 out in front of the natural log. So now we have parentheses 2x minus 1 times natural log of 5, remember that's just some number, equals natural log 2.5, that's just some other number. So now we'll follow the usual steps to isolate that x. First, we could divide both sides by natural log of 5. That puts 2x minus 1 by itself. As another step, we could add 1 to both sides. And as a final step, we could divide all of what's on the left and all of what's on the right by 2. Again, this is what we would call an exact answer. There's no need to simplify or try to find a decimal value unless we're in context of some kind of a word problem or unless we are asked for a decimal answer. Let's solve some logarithmic equations. This is similar to some problems we did in the last section. We have log of quantity x minus 6 equals 2. To undo the log, we need to remember what its base is. When we do not see a base written by a log, that means it's the common log, the log base 10. So let's raise both sides as a power of 10. And when I write this, I like to write the 10 very large compared to the other parts of the equation. That way I'm not confusing this 10 to the second power and thinking that it is 10 times 2. By property of logs, the left side simplifies to x minus 6. Essentially, the 10 and the log base 10 are canceling each other out. So we now have x minus 6 equals, and then 10 squared simplifies to 100. If we add 6 to both sides, we're done. X is equal to 106. In the last section, we never dealt with log base 6, and we never dealt with two logs on the same side of the equation. Our first step is going to be to combine these logs. Remember that there's a property of logs that lets us turn addition of separate logs into a single log with multiplication. Log base 6 of quantity x plus 2 times quantity x minus 3. Now we're going to raise both sides as a power of the base. Well, in the past, we've used 10 as a base and e as a base. This time we're going to use 6 as a base. 6 to the left side of the equation equals 6 to the right side of the equation. 6 and log base 6 can be thought of as canceling each other out, leaving us with x plus 2 times x minus 3. 6 to the first power on the right side simplifies to 6. Now we have a quadratic to solve. We're going to FOIL the expression on the left to get x squared minus x minus 6. With quadratics, we like to get everything on one side of the equal sign equal to 0. So let's subtract 6 from both sides, giving us x squared minus x minus 12 equal to 0. Can we factor that? Yes. From each of these, we get a potential solution. Either x equals 4 or x equals negative 3. But when we solve a log equation, we need to check each answer back in the original equation. Make sure that neither answer is causing us to try to take the log of a negative number. Remember that log is a function that is only defined for positive numbers. Well, if we look back to our very original equation and try an x equals 4, we're asked to take the log base 6 of 4 plus 2. No problem there. Log base 6 of 4 minus 3. Again, not a problem. But if we try to plug in x equals negative 3, we're asked to take the log base 6 of negative 3 plus 2. That would be trying to take the log of a negative number. Or over here, log base 6 of negative 3 minus 3. That's log of a negative number. That is undefined. So we're going to have to throw out the answer x equals negative 3. Our only solution is x equals 4. This equation has natural log on the left side, 2 natural logs on the right side. What should we do? Well, let's simplify the right side first. 2 separate logs being added can be turned into a single log with multiplication. So the right side simplifies as ln of 5x minus 15. Notice that I distributed 5 times x and 5 times negative 3. Now recall that ln, or natural log, is the log base e. So we're going to use e to cancel out natural log. Raise both sides as a power of e. E and natural log will cancel out on the left side. E and natural log will cancel out on the right side, just leaving us with x plus 17 equals 5x minus 15. So we'll get all the x's on one side, all the numbers on the other side. 4x equals 32. Divide both sides by 4, and we have our solution. And going back to check, natural log of 8 plus 17, no problem, taking the log of a positive number. Natural log of 8 minus 3, also taking the log of a positive number. So the solution 8 should work. Let's see a couple of applications where solving an exponential equation is necessary. First application involves compound interest, compounded n times per year. The question is, how long will it take an investment of $6,000 to double if it is invested at 3% interest compounded quarterly? First, we need to set up an equation using all the numbers involved. We're going to start with a P, principal of 6,000, R, interest rate 0.03, and N is going to be 4 per quarterly, 4 times per year. That makes our equation 12,000, which is double of 6,000, equals 6,000, parentheses 1 plus 0.03 over 4 to the power 4t. Our job is to solve for this t up here in the exponent. Our job is to solve for this t up here in the exponent. Our first step should be to isolate the exponential expression. To do this, we need to divide both sides by 6,000. We'll get 2 is equal to, and I simplified that parentheses to 1.0075 to the 4t. Do not multiply the 6,000 times the 1.0075. That would be contrary to the order of operations. We do not multiply and then apply a power. Our first step must be to divide by 6,000. Now we're ready to continue the problem by taking the log of both sides. I'll use natural log as I usually do. Natural log of 2 equals natural log of 1.0075 to the 4t. That's going to allow us to bring that exponent 4t in front of natural log 1.0075. Now we can write the equation ln of 2 equals 4t times ln of 1.0075. Remember that ln of 2 is just a number, and so is ln of 1.0075. So is 4 for that matter, so we can divide both sides by 4 times ln of 1.0075. Now, since we are doing a problem in context, we actually want to figure out the decimal version of this number. If you asked your accountant how long you need to leave your money in the account, and your accountant told you ln of 2 over 4 times ln of 1.0075 years, you would look at him a little bit funny. So you need to get out a calculator and figure this out. And we don't need to know individually what natural log of 2 is or natural log of 1.0075. Just let the calculator do the calculation all in one step. So start with ln of 2, be sure to close parentheses, divided by, and now open a parentheses for the entire denominator, 4 ln of 1.0075, close parentheses for natural log, close parentheses for your denominator. The answer is about 23.19 years, which I would round to about 29.2 years. For our last example, we're going to use the continuous compounding formula. The question is, at what rate of interest will an investment double in 6 years? Now, this question may seem a little vague because they didn't tell us the amount of money to start with. That is the principal. We don't have a number to use for P. But if you noticed in the last example, 6,000 doubled to 12,000. The first thing we did was we divided both sides by 6,000. Well, we can just start with the simplest P value, that is 1, and have it double to 2. This is what we'd get to even if we started with 6,000 doubling to 12,000, or 500 doubling to 1,000, or 10 million doubling to 20 million. The first step would involve dividing both sides to get 2 on one side and 1 on the other side. Our first step will be to take the natural log of both sides. Natural log of 2 equals natural log of e to the 6r. This allows us to bring the 6r out in front of natural log e. Now, the nice thing about continuous compounding is that we're using the base e, and so natural log of e turns out to be 1. So dividing both sides by 6, we'll get r by itself. And again, this is a case where we want to put natural log of 2 over 6 into a calculator to find an approximate value. Do natural log of 2, close parentheses, divided by 6, and we get a value of 0.1155245301. 0.1155 is the same as the percent 11.55. Hopefully these examples will be helpful as you go out and try to solve some exponential and log equations yourself. Thanks for watching this video, and we'll see you next time.